My name is Pankaj Sinsinwar. Welcome to my channel Maths with Pankaj sir. So today this is part 2 of permutation and combination. So we will be continuing more questions from this topic, and we have solved 12 questions in part 1 of permutation and combination. So without wasting any time, we will go to the 13th question. But before that, let me tell you, whenever question appears on your screen, pause the video, read the question first, and then go for the solution. Then this will be helpful because solution will not take much time. So to understand the solution and to learn more, you have to first read the question carefully and then go for the solution. So now let's go to question number 13. Read question number 13. A committee of 6 people is to be chosen out of 9 women and 5 men. We have to select 6 people. Now check the condition. Find the number of ways in which 6 people can be chosen if there must be more women than men on the committee. So more women must be there. It can be either it can be 6 women and 0 men, or this can be 5 women, 1 man, 4 women, 3 men. So it can never be 3 women and 4 men because number of women must be greater than number of men. So for this, I have to select 6 women out of total 9 women in 96 ways I can choose, and 5C0, 0 men out of 5 men. For the second case, I have 9C5 and into multiplied by 5C1, and I can choose 4 women in 9C4 ways and 3 men in 5C3 ways. So if I ask you total number of ways, then it is sum of all the above. This is total, and you have to do it by yourself. My objective is to introduce you as much concepts as possible, new introduction to new questions. So let's move to part B of 13th question. Read part B. 9 women and 5 men include a sister and a brother. Find the number of ways in which committee can be chosen if the sister and the brother cannot both be on the committee. So this can be solved by 2 methods. I will explain you both the methods. First one is method 1, that is easier one, that number of ways in which sister and brother cannot both be on the committee. It is total number of ways minus sister and brother together. So total number of ways in which 6 people can be chosen out of total. Total is 9 plus 5, which is 14. So total is 14C6. And now, if I have chosen sister and brother together, then 2 people are already selected. Now I can select remaining 4 people out of remaining 12 people in 12C4 ways. 12C4. So this is my final answer. This is method 1. Now we will go to method 2. Method 2 is also easy with some extra calculation. So brother and sister, they should not be on the committee together. So case 1 becomes when brother on the committee, brother is in the committee. So if brother is in the committee, so I can choose, I have already chosen the brother, so I can choose remaining 5 people from the remaining 12 people. I am not including the sister, as I have told you, only brother is in the committee. So I can choose 5 remaining people out of 12 in 12C5 ways. So number of ways equals to 12C5. Case 2, sister in the committee. So if I ask you number of ways, again it is same. If sister is selected, I can select remaining 5 out of remaining 12, excluding the brother. In 12, say 5 ways. And the last one, neither of them is in the committee. So if both of them are not in the committee, now I have to select all the 6 people from the 12 people, and I have 12 C6 ways. So to find total number of ways, I will just simply add these 3. This is my second way of calculating. I hope you understood. Let's move to the next question. Read this question number 14. Find the number of different arrangements that can be made of all the 9 letters in the word cameraman in each of the following cases. First of all, if there are no restrictions. So I have C, repeating 3 times, and then M repeating 2 times, and then I have R, E, and N. So I'll write C here only. So I have 3 A's which are repeating and 2 M's which are repeating. Total letters I have 9. So I can write total ways equals to 9 factorial upon 2 factorial into 3 factorial. Let's move to next question. The A's occupy first, fifth, and ninth position. First, 2, 3, 4, 5. This is A. 6, 7, 8, 9. So this is also A. Now, these 3 positions are fixed. These 3 positions are fixed and these cannot rearrange. Now, I am left with 1, 2, 3, 4, 5, and 6. Now I am left with 6 positions. So these 6 positions can arrange themselves in how many ways? 6 factorial ways. So total ways equals to 6 factorial upon, in these 6 letters or 6 spaces, somewhere I have 2 m's also. Somewhere I have 2 m's as well. So for this, I will write divided by 2 factorial. These 3a will not arrange themselves. So let's move to the next question. Read third part. There is exactly one letter between the m's. M, one letter between m, and then again m. 3, 4, 5, 6, 7, 8, and 9. So the remaining these remaining letters, excluding the 2m, can arrange themselves in how many ways? These can arrange themselves in 7 factorial upon, as we have 3 a's as well, so I will write upon 3 factorial into, now these m's can take 7 places. These m's, 8, 2, 3, 4, 5, 6, how much? 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have 9. This m can take how many places? 1, m. So 1, 2, 3, 4, 5, 6, 7. Now m can take 7 places, so I will multiply this by 7. See, to understand this, the arrangement can be m/m and the remaining spaces, or it can be m-m and remaining spaces, or it can be m-m and remaining spaces. So I hope this is clear now. So how many possible ways are there? In total 7. Let's move to the next question. Read fourth part. 3 letters are selected from 9 letters of the word cameraman. Now 3 letters are selected from 9 letters. So find the number of different selections if the three letters include exactly 1M and exactly 1A. Exactly 1M and exactly 1A. So 1M, 1A is fixed. Now I have to select one more letter. So I have to select one more letter from the remaining alphabets. Let me write how many alphabets I have. I have two M's, three A's, and C, E, R, N, 43729. Okay, so I have to select one out of these four letters from the four remaining. These are four remaining letters. So I have to select one alphabet from this and one remaining. This is the only possibility that I have. So I can do this in how many ways? Four, C, one number of ways. I have not taken, as I have selected exactly 1M out of 2 and 1A, exactly 1A out of 3 A's. I have not taken 2C1 and 3C1 because A's and M's are identical. That's why. Because A's and M's are identical. That is why I have not written, let me clarify, 3C1 and 2C1. I have not written this because 3 A's are identical and 2 M's are also identical. So I will not write this. Read this 15th question. Freddy has six toy cars and three toy buses, all different. He chooses four toys to take holiday with him. In how many different ways can Freddy choose four toys? So Freddy has to choose four toys. Total number of toys कितने? 6 plus 3, 9. So Freddy can choose four toys out of 9 in how many ways? 9C, four ways. So let's move to next question. How many of these choices will include both his favorite car and his favorite bus? So, six toy cars and three toy buses. Six toy cars and three toy buses. Now, his favorite bus and favorite car must be included. So now he has to choose two more toys out of remaining. Um, Total were nine. So two he has already selected. So he is left with seven toys, and he can select the remaining two toys in how many ways? 7C2 ways. Let's move to the next question. Freddy arranges nine toys in a line. Find the number of possible arrangements if the buses are all next to each other. So all the buses are together. This is bus 1, 2, and 3. So it is given that these buses must be together. Now 6. So I have 6 other toy cars. So I can arrange these toys in how many ways? Taking all the buses as one object or one entity. So I have total how many? 1, 2, 3, 4, 5, 6, 7. So I can arrange these in 7 factorial ways. Also, I can arrange 3 buses in 3 factorial ways. So I will multiply it by 3 factorial ways. This is my total number of ways. This was the question. Let's move to the next question. See, this question is interesting. Find the number of different possible arrangements if there is car at each end and no buses are next to each other. 1, 2, 3, 4, 5, 6, 7, 8, 9. So if there is car at each end, this is fixed. So these two cars, C1 and C2, these two cars can be arranged in, these two cars and selected and arranged in total arrangements. In how many cars do I have? I have three buses and I have six cars. So these two cars out of six can be chosen as 6 P2. Why I have written P2? Because C1 and C2 can interchange, right? So that is why I have written 6P2. I have not written 6C2 because C is for selection and P is for arrangement. As C1 and C2 can arrange between them, so I have written 6P2. Now, the remaining toys remaining 7 toys can arrange themselves in how many ways? 7 factorial ways. How many ways? 7 factorial. But wait. It is given that no buses are next to each other. No buses are next to each other. So if two cars are already selected, so I am now left with 4 cars. So this is C1, C2, C3, C4. So this question will be solved by spacing. So no buses. Three of the buses, these three buses must not be together, and not even two buses can be together. So all of the buses must be, uh, you know, at different positions or different locations, but not together. So this question will be solved by spacing. I have 4 cars left, so I can arrange 1, 2, 3, 4, 5. I can arrange 3 buses in how many locations? 5 locations. And these remaining 4 cars can arrange themselves in how many ways? These 4 cars can arrange themselves in 4 factorial ways, and I can choose 3 spaces out of these 5 spaces in 5C3, but I can arrange the 3 buses. For example, I have taken B1, B2, and B3 in the spacing, so I can arrange the buses as well. So I will write 5P3. So this selection and arrangement can be done in 5P3 ways. So I will write 6P2 into 4 factorial into 5P3 total ways. So this question was really interesting. Now read question number 16. A group of 6 teenagers go for boating. There are 3 boats available. One boat has room for 3 people, one has room for 2 people, and one has room for one person only. Find the number of different ways in which 6 teenagers can be divided into 3 boats, divided between 3 boats. So we have in total 6 teenagers, and now this is boat 1, this is boat 2. In this boat, I can seat 3 passengers and 2 seats for boat 2 and 1 seat in boat 1. So I can select 3 passengers or 3 teenagers out of 6 in how many ways? 63 ways. I can select 2 passengers out of the remaining 3 in 3C2 ways, and I can select 1 out of the remaining 1 in 1C1 way. So this is my total number of ways. Final answer. Part B. Find the number of 7-digit numbers, different arrangements of the 7-digit number which can be formed from the 7 digits of 2, 2, 3, 3 in the following cases. The odd digits are together and even digits are together. So first of all, I'll write odd digits. So I have in this box odd digits. I have even digits. So 2, 2, 8 are even. 3, 7, 7, 7. These are odd. So these odd digits can be arranged in 4 factorial upon 3 factorial ways, and these 3 even digits can arrange themselves in 3 factorial upon 2 factorial ways, as there are 2 2s and this have 3 7s. Therefore therefore total number of ways will be multiplied by 2. Why 2? Because this even and odd digit can also interchange. It can also be like here odd, here even, and here odd digit. So we will multiply total number of ways by Let's move to the next question. In this part, they're asking twos are not together. So we had numbers 3, 7, 7, 7, and then 2, 2, and 8. So twos are not together. This can be calculated using total possible arrangements, total minus together. Total will be 3 plus 4, 7. So 7 factorial upon how many ways? 2 factorial into 3 factorial minus together. Number of ways in which twos are together. So see, I'll write here. If twos are together, so I will take them as one digit, and remaining digits are 3, 7, 7. This is one digit, 7, and 8. So I can arrange these digits. The total number of digits are 2, 3, 4, 5, 6. So 6 digits can be arranged in 6 factorial divided by, as we have 3, 7, so 3 factorial. I have taken both the 2's as 1. So minus 6 factorial upon 3 factorial ways. Let's move to the next question. Students, read question number 16. Mr. and Mrs. Keen and their 5 children. Mr. and Mrs. Keen with their 5 children all go to watch a football match together with their friends, Mr. and Mrs. Uzuma, and their 2 children. Find the number of ways in which all the 11 people can line up at the entrance in each of the following cases. So there are 11 people, and the first part is Mr. Keen stands at one end of the line and Mr. Uzuma stands at the other end. So Mr. Keen is fixed at the one end, and Mr. Uzuma is fixed at the other end. So, but they can also interchange. So Mr. K, yeah, for Mr. Keen and Mr. Uzuma can interchange themselves. So, and remaining 9 people in between 1, 2, 3, 4, 5, 6, 7, 8, 9. So, remaining 9 people in between can arrange themselves in how many ways? 9 factorial ways. And these two can arrange themselves in 2 ways. So, 2 factorial ways I will write into 2 or 2 factorial, which is all same. So, total number of ways are 9 factorial into 2. Let's move to the next question. The 5 Keen children all stand together and Ujuma children both stand together. So Mr. Keen and Mrs. Keen. Now I have 5 children of Keen family. These stand together. Now for Uzuma, I have both the children of Uzuma family stand together. So U1, U2 stand together, and this is Mr. Uzuma and Mrs. Uzuma. Let me write it in complete. Mrs. Uzuma. So if I take them, Keen children and Uzuma children, if I take them as one separately, so in total I have 1, 2, 3, 4, 5, and 6 people. These 6 can arrange themselves in these 6 can arrange themselves in 6 factorial ways. 6 factorial ways. But also 5 Keen children will arrange themselves in 5 factorial ways, and 2 Uzuma children will also arrange themselves in 2 factorial ways. So this is my total number of arrangements. Let's move to the next question. Now read question number 17. Find the number of ways a committee of 6 people can be chosen from 8 men and 4 women if there must be at least twice as many men as there are women on the committee. At least twice men must be there. And it is given that there are 8 men and 4 women, and 6 people are chosen. So it can be 0 women and all the 6 are men, or it can be 1 woman and 5 men, 2 women and 4 men. So these are the only possible outcomes. I will write number of ways for each one. It is we have to select 0 women out of 4, so it is 4C0, which is one only, and 8C6, 4C1, and 8C5, and 4C2, and this was easy. So we will add these all the number of ways, which will be our final answer. Now we will add all the possible number of ways and we will get our final answer. Let's move to the next part. Find the number of ways a committee of 6 people can be chosen from 8 men and 4 women if two particular men refuse to be on the committee together. So this can be solved total number of ways minus 2 particular men are on the committee together. On the total number of ways in which 6 can be chosen out of 8 men, 8 men and 4 women. So total 12 is 12C6 ways minus 2 particular men are on the committee together. So if 2 men are on the committee together, so they are already selected. Now we have to select 4 more people out of the remaining 10. So which is 10C4, and this is our final answer. Let's move to the next question. Read this question. Find the number of different ways in which 12 letters of the word steeplechase can be arranged so that all the 4 E's are together. So we will take all the E's as 1. So there are 1, 2, 3, and 4. 4 E's, 2 S, and T is just 1, P, L, C, H. 3 plus 2, 5, plus 2, 7, plus 4, 11. I missed just one more word, A. So I have 4 E's, 2 S, and ATP, LCH. So I have to take all these E's as 1 or together. So this is 1, and here I have 2, and this is 6. Total number of letters becomes 6 plus 2, 8, plus 1, 9. So total number of ways are 9 factorial divided by 2 factorial. This is for 2S. Let's move to the next question. Part 2. Find the number of different ways in which all the 12 letters of the word steeplechase can be arranged so that SSS are not next to each other. So there were 4 E's, 2 S's, and ATP LCH. ATP LCH. Now, S's are not next to each other. So we can find number of ways in which total number of ways minus are together. So total number of ways are 12 factorial divided by 4 factorial into 2 factorial minus two s's are together, so I can take s as 1. So this is 6, this is again 4. So 6 plus 4, 10 plus 1, 11. So when s's are together, it becomes 11 factorial divided by 4 factorial. This is for 4 e's. So this is number of ways. Let's move to the next question. Read this question, part 3. 4 letters are selected from 12 letters of the word steeplechase. Find the number of different selections if 4 letters include exactly one S. 4 letters include exactly one S. I had selections out of 3E, no, 4 E's, 2 S, and ATPLCH. ATPLCH. So, different selections if the 4 letters include exactly one S. So, there are one S, and it can be 1s and 0 e's, or it can be 1s with 1e, 1s with 2 e's, and 1s with 3 e's. Okay, so we have to select exactly one s, so we are done with it. And for total number of ways, we will add them up, and this will give us total ways. Let's move to the next question. Read question number 19. In how many different arrangements are possible of the 9 letters of the word corridors? So we have two O's, and we have three R's, and C, I, D, S. So 4 letters, 3 R, and 2 O's. 4 plus 3, 7 plus 2, 9. So total letters are 9. How many different arrangements are possible? Therefore, total arrangements are 9 factorial divided by 2 factorial into 3 factorial. Let's move to the next question. How many different arrangements are there of the 9 letters in the word corridors in which the first letter is D and the last letter is R or O? So it is given that first letter is D and last letter is, let's say last letter is R. This is case 1. And first letter is D again and last letter is O. This is case 1. Case 2. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So the remaining 7 letters, as these positions are fixed, D and R, these are fixed. So now I can arrange the remaining letters. Let me write the remaining letters. There are 2 O's, 3 R's, and C, I, D, S. So one R is fixed, and one D is also fixed. So now I have 2 O's, 2 R's, and 3 remaining. So these can be arranged in how many ways? So 7 factorial divided by 2 factorial into 2 factorial. And for this, 2 O's, 3 R. If D is fixed and O is also fixed, so now I have 1 O, 3 R, and 3 remaining. So these can be arranged in how many ways? 7 factorial divided by 3 factorial for 3 hours which are repeating. So I will add these two. Therefore, total arrangements will be 7 factorial, 2 factorial into 2 factorial plus 7 factorial upon 3 factorial. These are number of ways. Next, read question number 20. A sports team of 7 people is to be chosen out of 6 attackers, 5 defenders, and 4 midfielders. The team must include at least 3 attackers, at least 2 defenders, and at least 1 midfielders. So in total, we have 6 attackers, 5 defenders, and 4 midfielders. And we need at least 3 attackers, at least 2 defenders. For a team of 7 people, I need at least 3 plus 2, 5, and 2 midfielders. So total becomes 7. Now, it can also be 3 attackers and 3 defenders and 1 midfielder, because at least 1 midfielder must be there. Now, 4 defenders cannot be there with 3 attackers, because it will be like then it will have 0 midfielders, which is not the condition. So now I have 4 attackers with 2 defenders and 1 midfielders. That's it. No more options. So the total number of ways now become 6C3. 3 attackers can be chosen out of 6 attackers and 6C3 ways. 5C2 and 4C2. 6C3, 5C3 and 4C1. 6C4, 5C2, 4C1 ways. You add them and here you get total ways. Let's move to the next part. The team of 7 is chosen to travel to a match in 2 cars. A group of 4 travel in 1 car and a group of 3 travel in other car. In how many different ways can the team of 7 be divided into group of 4 and 3? So in 1 car there are 4 people can be seated, and in another car 3 people can be seated. So I can select 4 people out of 7 in 7C4 ways. I can select 3 people out of the remaining 3 people in 3C3 ways. So therefore total number of ways is 7C4 into 3C3. This is 7C4 and 3C3. Let's move to the next question. See, this is question number 21. A selection of 3 letters is to be made from 8 letters of the word collider. How many different selections of 3 letters can be made if there is exactly one L? So in collider, we have 2L and we have nothing repeating letter CO, I, D, E and R. So how many different selections 3 letters if exactly one L? So if there is exactly one L, Remaining two letters can be chosen in how many ways? This is 3 plus 3, 6 letters. In 6, see, not 3, 62 ways. Let's move to the next question. How many different selections of 3 letters can be made if there is no restriction? If there is no restriction. So, if there is no restriction, then letters can be formed with no L, case 1, case 2, 1L, case 3, 2L. So, 1, 2, 3, 1L is fixed, and here we have 2L. So, these 3 letters can be chosen in out of 6. So, these 3 can be chosen out of 6 in 6C3 ways. These 2 letters can be chosen out of 6 in 6C2 ways, and this can be chosen in 6C1 number of ways. We will add them up, and that will be our final answer. Move to the next question. This is question 22. The digits 1356668 are arranged to form 7-digit numbers. How many 7-digit numbers have all the even digits together and odd digits together? So in total we have how many letters? Digits? 7 digits. With even digits together. So 6, 6, 6, 8. These are together 1, 3, 5. These digits are together. So I can arrange these 4 digits in 4 factorial upon 3 factorial ways. I can arrange these 3 digits in 3 factorial ways. Also, even and odd can interchange, so into 2 number of ways. Let's move to the next part. How many 7-digit numbers are even? So, first of all, let me write the digits. 1356668. So digits are 1356668. For the number to be even, either the last digit is 8 or the last digit is 6. So if the last digit is 8, so this will not rearrange. I can arrange this 6 digits in how many ways? 6 factorial. With as 8 is already cancelled, now I have 3 repeating 6's. So 6 factorial upon 3 factorial. In this part, I have 1356668, and as 6 is already fixed, so I will remove 1 6 from here, and now I can arrange these 6 digits in 6 factorial divided by 2 factorial because of 2 repeating 6's. And now for total number of ways, I will just add them up. 6 factorial upon 3 factorial plus 6 factorial upon 2 factorial number of ways. Let's move to the next question. This is question number 23. Read the question. Find the number of different ways in which 9 letters of the word mincemeat can be arranged in each of the following cases. First, if there are no restrictions. See, there are 2M and there are two E's, and INCAT. So this becomes 2M, 2E, and 5 remaining or different letters. Now total number of arrangements equals to 9 factorial divided by 2 factorial into 2 factorial ways. Let's move to the next part. No vowel AEI is next to another vowel. So the question was MMEE INCAT. M M. So AEI are vowels and are not next to each other. No vowel is next to each other. This question, no vowel is next to each other. So this will be solved using spacing. In this question, it is clearly mentioned that not even two vowels can be together. Not even two vowels can be together. So we will not solve this by total minus together, because it is not saying that three vowels must not be together. It is saying no vowel must be next to each other. So only spacing can solve this question. If I remove three vowels from this, A, E, and I, if I remove three vowels, two E's, and I, and A, so basically I am left with 2, 3, 4, 5, 5 letters. So I am left with 1, 2, 3, 4, 5. M, M, N, C, T. I have spaces in between them where I can place the vowels. So I have four vowels: E, E, I, A, E, E, I, A. I have four vowels. Also, these five letters can arrange themselves in 5 factorial upon 2 factorial ways, because we have 2 repeating M, and I can place 4 alphabets. I can place these 4 alphabets at 1, 2, 3, 4, 5, 6, at 6 spacings in 6. Wait, this question is tricky. Now we have to select 4 spaces, and we can arrange these 4 alphabets at 4 spaces in 64 ways. But also in this question we have 2 E's, 2 repeating vowels E's as well. So I will divide it by 2 factorial. So this will be my final answer. So this will be my final answer. Total arrangements. Let's move to the next part. This is question number 24 and the last question for today. In each of the videos, we will be solving around 12 questions. In the first video, we solved 12 questions, and in this video as well, we have solved 12 questions. So, find the number of ways in which 9 letters of the word Australia can be arranged in each of the following cases. All the vowels A, I, U are together. So, in Australia, I have 2 A's, 3 A's, and U, S, T, R, L, I. So 6 letters, 3 letters. Now it is said that A, I, U vowels are together. So A, I, and U, these are together. So I will take them as one object or one alphabet, U, I, and remaining are S, TRL. Therefore, total number of alphabets I have is 1, 2, 3, 4, 5. Now I can arrange these letters in how many ways? 5 factorial. But wait, 5 factorial ways. But here we have 3 A's and I and U. So these can arrange as well. So these can arrange themselves in how many ways? 5 factorial upon 3 factorial ways due to 3 A's. So this A, U, I, these can also arrange themselves in 5 factorial upon 3 factorial ways. So this is done for today, and I hope you learned from this solving of past papers. We will continue this in the next upcoming lectures, and see you in the next video. Bye bye. Thank you so much.